So I'm very glad today we have a speaker of our own member of the Mathematics for Public Health Network, a member of our own modeling community, and a member of the Canadian National Modeling Development. Michael does not publish intensively, but every paper he publishes really point out a lot of lay down some of the foundation for future development. It's including the compound matrices for global dynamics, dynamical systems, especially with application to mathematical biology, the construction of globally approved function for global stability of epidemiological models. And I heard multiple times Michael has recently sent us a warning, and I just want to call your attention to the participant that when Michael speaks, we better pay attention, especially his warnings. So
Okay.
given that, Michael. Yeah.
Okay, thanks. I guess I'll share my screen first. That looks all right to everyone?
It's good for me.
Okay, so thanks very much, Jianhong, for the kind introduction. Well, I guess mathematics for public health, I guess that's really, we're trying to use mathematical theories and tools, modeling tools to solve public health problems. And it's equally important that we constantly improve our theory and tools to meet the challenges, new challenges from public health problems. And it's the latter that have been occupying my mind for the past 2 years. I was just puzzled why sometimes, a lot of times, that the model don't perform well in the predictions. So I try to find the mathematical answers to it. And then I find myself asking very basic questions, is like, what is an epidemic? Or how is an epidemic different from endemic diseases? So it sounds really a silly question, but obviously I'm not looking for a definition for epidemics. I'm more concerned because when we see an epidemic, do we know it? So here I show you a set of data, which I got it from WHO websites. I'm not telling you which disease this is. This is just, case data over the years, and I'm not saying which country this is. So this is the data from 2013 to 2018, that's 6 years. And obviously this is sort of like a seasonal, and every year it seems to be very similar, sometimes higher, sometimes lower. And obviously it's endemic because it happens every year. And this is not influenza, okay, not influenza. So the question for a modeler, when you see this, we're asked to model this, and then the question would be, is this endemic disease or is it an epidemic disease? Well, depends, right? I don't think we would all agree with one answer or the other. If it is endemic, and then what would be the best way? Obviously, it's endemic. It comes back every year. What would be the best way to model it? Now, there's kind of two purposes of modeling. One purpose is just for mathematical reasons, for mathematical understanding of the mechanisms that produces these data, disease process, the transmission process that produces this set of data. So, for example, if you think this is seasonal, and then you can look at it, maybe this is some kind of periodicity going on. So there are really good tools to study that for long term. And you could also looking at impacts of some intervention on the R0 so that it can reduce R0 gradually to below 1. And then these things will tend to reduce the cases in the long run under control. And then there's another purpose, especially for our networks the objectives here is to look at the public health concerns. So for public health purposes, things might be different. Okay. So this might be better modeled as the annual epidemic instead of thinking this is a long-term endemic disease. Because if you look at that, you think about it, the people on the ground, okay, they face these challenges, public health people, every year at the beginning of the season, they would have to think about how bad this year is going to be, how do we manage it? They're not thinking about next year. So they got so many challenges just this year at the beginning, or even before the beginning, right? So there's a lot of planning, all kinds of things have to do. They worry if their hospitals get overwhelmed, whether they have to cancel surgeries here. It's already happened here during COVID. So then why do we have to tell them that this is an endemic disease? We need to look at how, many years down the road, that's not really their immediate concern. So if we have to address that kind of concern, for example, how serious this year epidemic is compared to usual years, and when will the peak happen, how high the peak is, this has a lot to do with the public health capacity. And so these things are on their mind, and they would like our model to provide some guidance to them so that they can do better planning. Now, if we do address those kind of concerns, maybe this should be treated as an epidemic 1 year at a time. So even for endemic disease, depending on the nature of things, we treat this much, I think for public health concerns, this is the epidemic for this year. And the next year, it will be another epidemic. Right? This is the same viewpoint we take for influenza. We predict for each season. So now, if you agree with me on that, then the question would be, what are the mathematical tools we have in our theory, in our toolbox, to address these kind of concerns? What's the severity, and when will the peak occur? How high will the peak be? Can we predict these? Before the epidemic occurs, or just shortly after the epidemic occurs, so that we get some data? Can you predict ahead of time when the peak is? So what kind of theory do we have here, right? Now, if you think about the standard tools for infectious diseases, we use these in publications, in our, we teach students about these. We have a good tools to compute R0 using next generation matrix methods. We have the standard finding equilibria, linearization, stability analysis, and also bifurcation analysis. And also we have a very good way to do simulations, even fitting model to data, estimating parameters so that we get good simulations. But these things, if you think about it, these are really, stability analysis, equilibrium, these are really at the very far time, large time. It's not really beyond a epidemic, right? So these are really suitable for study asymptotic behaviors of an endemic disease. So these are not quite suitable or developed address questions concerning epidemic. Epidemic is really simple. It goes up and peak and down, right? There's not much of a bifurcation that going on with this, okay? And but the question is hard, and it is important for even this past, from fall to now, we know there's these tri-epidemic going on, RSV, influenza, and COVID, and our hospitals that are overrun, the emergencies are packed, children are infected. So long before that, even during the summer, the Alberta Health Services, they kind of anticipated this thing going to happen. So they asked us, can we give them a little bit of lead time on the peak time and seriousness of the influenza, for example, and COVID, so that they can kind of plan, for example, if there's a lot of staff shortage, or if there's a lot of people crowded into hospitals, they have to cancel surgeries. So with very serious consequences. So those are the things they think is very, very important. We can be a good prediction. We can be very big help to the planning. So, okay, so this is the background of doing this. So let's just recall what we know exactly about epidemics in terms of the mathematical theory. So I'll just use a very simple model. You could do a more complicated models, but the theory basically is captured by an SIR model. And in order to produce epidemic curves, we know you ignore the births and deaths. So you got SIR, S is susceptible, I is infected, and infectious, and R. And the criticism for SIR, of course, is that we assume people are infectious right away after the infected, but that's not the way I see it. For example, people say you should use SIR, but the transmission parameter beta is the average over all individuals, right? Infected individuals. So it's an average number. So if people are in the latent period, they just have a infectivity 0. So you can still do the average. Okay, I'm not ignoring that latent period. It's just latent people have a 0 infectivity. I still do the average. So this is SIR. Okay, and then we know the basic reproduction number. The basic reproduction number. Where did I go? Here. S0 is the initial susceptible size, and susceptible should also be taken as at risk. If you quarantine a lot of people, those people are susceptible, but they're not at risk. So that shouldn't be part of your consideration. Okay, so S0 and the rho parameter here is understood as critical community size. To sustain epidemic, your initial population, susceptible population, should be larger than this number, critical size, for epidemic to occur. If it's below it, there is no epidemic. Okay? So this is the things we understand really well. So this is the susceptible would decrease, and then the infected, the red curve increases and peaks, and then when the susceptibles drop sufficiently, and then the peaks, and then declines, and then the recovered people become immune here. Okay, so if the epidemics are really short, you could assume that the acquired immunity is long enough to outlast the duration of the epidemic. For the COVID, we know that the immunity, the acquired immunity or vaccine immunity probably lasts more than 3 months. The typical wave of COVID is usually 3 or 4 months. So you could assume during that period, recovered people would be immune, okay, without getting reinfected. So this is the SIR. Okay, so all the mathematical theories are captured in this face portrait. Okay, so I plotted the orbits in the SI. This is the face portrait, right? Each curve is computed the orbit. So each point there is ST, IT. So we don't see time in this, we only see the orbit, okay? So here, I've taken the initial value, initial susceptible, S0, above the rho, even with a small infected I, small I, you would have an epidemic, it grows, I increases, S decreases, and to some point when S decreases till the rho value, the critical size, I reaches maximum. And then after that, I decreases. So this produces the epidemic curve. So this is in the standard textbook. We know that really well. And also, if you compare two different S0s, for example, this curve, we have a larger population, so the epidemic is larger, and then when the epidemic ends, there are always some susceptibles left. So these are called the final size, and the larger or higher epidemics would end up with a smaller final size. This is what we see from there. Even for the same S0, if you go up this way, if you pick this curve, which means same S0 but higher I0, higher initially infected will give you a higher epidemic. Okay, these are all very intuitive, and they all peak when S reaches this critical size. Doesn't matter where you start. The peak always happens when S0 reaches this critical size rho. And so basically what determines why it goes up and peak is the decline of ST. This is the driver, basically. You keep losing susceptibles to infection so that you lose the momentum. You lose we usually say you burn the fire. The firewood almost got exhausted enough, the fire diminishes. So that's the, but if you look at all these properties are really different. It's really different from the endemic diseases. For example, for endemic disease, it tends to go to endemic equilibrium when R0 is larger than 1. It doesn't matter what's the initial I0, as long as they're positive, they all go to the same equilibrium, right? I0 doesn't play that much of a role in terms of the reaching equilibrium, but here I0 does play a really critical role here. So this is really not quite the same theory as the theory for endemic diseases, right? So if we use those tools for endemic disease to analyze models that trying to capture the epidemic, I think it's somehow there's a mismatch here. Right? Now look at the role of R0. Okay, there's also a difference. For R0, for endemic diseases, R0 really is everything. We usually consider if R0 is larger than 1, everything goes to the same endemic equilibrium, usually, most of the time. And if R0 less than 1, disease automatically go to 0 under control. So a lot of the intervention, the impact of intervention are discussed on how the impact on R0, okay? But for endemic disease, R0 really doesn't play that much of a role here. It's just that initially, if R0 somehow translated into critical community size, if that's smaller than your population, you would have epidemic. If it's larger than your population, then you're fine. You wouldn't see an epidemic. But then usually this threshold is always smaller than so we see a flu every year. We see, once we got a new variants of COVID, there will be a wave. So those threshold usually is no bigger than our population size. And but once the epidemic starts, if you recall, during the COVID, people continue to report R values during the epidemic. R value is still larger than 1. Or now R value is less than 1. We feel safer, right? And so this is something we call RT instead of a T, sort of with like indicating time. So only R0, we spend a lot of time estimating R0 only before the epidemic comes or at the beginning. Once it comes, we start looking at RT value. So what's the role of R0 for epidemics? Right? So that's a question for us to think about. Just a little bit more on RT. So what exactly a definition for RT? Okay, for simple models like SIR, there's a natural definition of RT that is just, you have R0 is the initial size of susceptibles over this critical size rho. You could replace that by ST. The ST decreases, so RT decreases. And so if RT is larger than 1, we can show IT increases, okay? And if RT is less than 1, it decreases. RT equals 1, that's exactly when S equal to critical size, it peaks. So RT in this way, defined in this way, kind of reflects different phases of the epidemic, okay? But then for more complex models, the R0, is usually the spectral radius of a next generation matrix. You can still replace all the S0s there to STs, but then does it have this property? Does it actually necessarily reflect these different phases of that? Now, if you ask a little bit more general questions of what is a reasonable definition for RT, rigorous definition of RT, and does it have these required properties? You would like RT to have these kind of properties so that when they see RT, they kind of know where we are during the epidemic, right? So I don't know. I think these things are unknown, but let me know if you think some people already have done some definitions and establish these properties. Say if you have a multiple group model, yeah, I'm not too sure, right? But then what a surprise is R0 in our traditional theory of epidemics, R0 really is a very powerful parameter for epidemics, okay? So this comes when you look at the final size. So the value of R0 actually determines the epidemic size or the final size, okay? Let me give the definition here. The final size is the number of susceptibles who escaped the epidemic. At the end of the epidemic, you look at how many people are not infected. This is what we call S infinity, right? And the epidemic size is just the proportion of the people who are infected. It's sort of the complement of the final size. So it's 1 minus the proportion of people who are left, okay? So I call it X. So the final size formula can be easily proved, derived by looking at this first integral. And it's saying this. So you see the R0 is related to S infinity. S0 is known. So if you know S infinity, you know R0. If you know R0, you know S infinity. So if you know R0, you can actually know the final size right away out of this relationship, okay? So you don't really have to know beta. You don't have to know gamma, right? If you know R0, if you estimate the R0, you know S infinity out of this. And that's a very, very powerful role, R0 plays. Right, you can predict right away. For example, 2 groups look at the same data. We might get a different beta and rho or gamma, these parameters, but as long as we have the same R0, we would predict the same final size. That's a really revelation to me when I look at that. Okay, I never realized R0 is so, but that sounds a bit too good to be true. I think, right? You start questioning, is that really correct? But based on the theory, this is the result. But it doesn't seem to match what we observe. So that's where it puzzles me. Okay. And then if you translate that final size formula to the epidemic size, the proportion of infected, you kind of get this relation. Then X here is the proportion of the infected for a particular R0. You can plot X as a function of R0. Okay, this defines that function implicitly. You can plot that. So I pick different values R0 horizontally, and then the vertical axes are the corresponding final size. You kind of plot it. You get this curve. I'm sure many of you have seen this curve. Now, COVID, we know, is somewhere at R0 at the beginning, the first wave. I'm not sure what the R0 for Omicron, but at the beginning, right? It's somewhere between 1.5 and 4-ish. So let's pick a 2, okay? Suppose R0 is 2, what will be the final size our model predicts? Here, 80%. So if R0 is 2, which is very reasonable for a COVID first wave, we would predict 80% of our population at risk would be infected. If it's sort of there's a lot of noise in the data, if you predict the interval, maybe the lowest estimate is 1.5. If your R0 is 1.5 and the corresponding final size, 60%. So if you recall at the beginning of the COVID, 3 years ago, around this time, there are a lot of projections that, if we don't do anything, 60% of the population will be infected. And this is exactly why, okay? But 60% is a bit too much, right? Even for Omicron, our Omicron wave, usually during that time, there was not much of a public health response anymore. We don't have a 60% population. I think right after the Omicron, there's a study out of the immunity study group that they look at the antibody tests from different regions in Canada. They say up to that time, and there are about 50% of Canadians are infected. This is after the first Omicron wave. So Omicron single wave doesn't really infect 60% of the people. So these kind of estimations are definitely over projection. Right? So that's sort of tell us that the theory as we have in the textbooks would over project things. Okay. So that just means that it doesn't have a predictive power. It captures the dynamics quite well, very clear, very simple, but can't use it to predict. You would over project. Okay. So that's so somewhere during the I was searching the internet, and I came across this article online magazine. It's called a Quantum magazine. It specializes on writings on mathematics and science. This particular article is by the journalist Jordana Kopelevich, and it's about 2 years ago. So she actually interviewed many modeling groups, different campuses in the US and also in Europe, and talked to the modelers about their experiences. And the conclusion seems to be a lot of frustration. People, the modelers have a very enjoyed, almost like a hero-like fame during the first wave, because the high projection really scared the public health people, so they shut down. So we have a very mild first wave, and that certainly is true in Alberta. And but then when the second wave comes, they feel, no, we can't predict the peak time. People have trouble. For example, there's, people agree that the peak of an epidemic could never be estimated until it has happened. So you can't really predict a little bit of before it. And attempting to predict plateaus of the epidemic curve over long term is just as fruitless. So these are really frustrations, and we shouldn't even try to estimate the peak or other landmarks of the epidemic curve until the number of infections is 2/3 way after that, you somehow know where the peak was. It's kind of depressing, and then But people are kind of puzzled about this. Why? Because our model can always fit the past data so well. You know, if you have a little bit of a piece of the data at the beginning of the epidemic, we could always fit this so well, but our projections are usually quite wrong. So this particular modeler, this Marubia, is from either Italy or Spain, says, well, these models are very illustrative of the underlying dynamics. They have no predictive power. So this is sort of as early as the beginning of 2021, people kind of realized these models as we have don't perform well, okay? So there's a lot of confusion and frustration. So that's when I start looking into why is that so? You know, we taught these theories, I taught these things over the years, for 10 years for my graduate class, and I never doubted anything, right? This is the best theory we get. So now there are two important issues captured in that article. Is first, you know, for models who give you good understanding of the underlying mechanisms that don't necessarily imply they can make accurate predictions. These are two totally different things. Okay, the same model not necessarily can do both, or if you can do one well, doesn't necessarily give you the other. So that's something that people realized. And then the second one is when our model can fit the path of reproduce path, why couldn't it predict the future? Okay, so yeah, so this is the thing I've been thinking as we were doing projections for Alberta Health. These things are always on the back of my mind. I think now I realize that it's our theory that actually failed at us. It's not really we didn't do something right. We all worked so diligently, tried so hard, but the theory is not adequate for doing real-time epidemics. Okay, so the final size relation, the curve, basically tell us our model couldn't predict. You always overproject. So that basically gave us the verdict that our models are good for underlying dynamics based on the asymptotic behavior, but they couldn't predict finite time accurately. Okay, and so the theories, in my mind, is inadequate. We need to revisit them to see what's missing if you want to do real epidemics, and how do we improve it. Okay. The second question over here is talk about fitting the past data and reproducing the past. So you have to talk about data. Okay, so that's where a lot of the problem. Okay, so let's take a look. So what is public health data? And does have a public health data play a role in modeling? Now, so public health data on notifiable diseases, if the disease is not notifiable, you wouldn't have any data because nobody reported. Okay, so the data we have are all on notifiable diseases and collected when individuals have some interaction with the public health system. For example, if someone never seen a doctor, never visited to the hospital, we have nothing on this person. So usually we have some record about someone is because you have some doctor visit, or you had a vaccine shot, or some other thing being taken into a hospital for emergencies. So it's really collected through individual interaction with. So there you see that there's a collection part on the public health side. There are also the individual behavior side. Why would someone voluntarily interact with the public health system? For example, if you during a flu season and you feel some kind of uncomfortable, I'm not feeling right, I probably got a flu. Would you see a doctor about it? It varies depending on the person. And most likely I wouldn't, because I'm consciously knowing the doctor can't do anything if I get the flu. There's no drug I can take to cure the viruses. So I say I'll tough it out. But then other people might just go. And then, so if you go there, and then the doctor would, ask you a lot of questions. If you suspect influenza, you would take a swab. And then the swab would be sent to the lab, and the lab tested. If the result is positive, and then the doctor would tell you. And then the same time, doctor report this to the to the surveillance system, and then they recorded, this is a case. Okay. If any of the step come back negative or failed, we don't have a case, even though you're infected. Okay. So that's what a case means. The case, the case, is someone who tested positive. That there's a lot of things going on in order to produce a case. I remember I talked to my good friend Ping Yan, who works for public health agency, and he said, for an infected to go to a case, you need a separate model for that. I am entirely agree. Okay, this is a very complicated process. Okay, but let's leave that for now. So I explained what's the case, right? And the cases are infected who get tested and tested positive and recorded. Okay, if the infected, like myself, if I get infected, but I never seen the doctor, never got swabbed and tested, I'm not a case, I'm just infected. So on any given day, okay, there are reported cases, but health services knows, or public health services knows, and they're infected that they don't know on any given day, okay? And maybe these people later become serious, they went to see a doctor, then got recorded, become a case later, but on that day, these people are not known, okay? This happens every single day, okay? That's how we see the case and the infected, okay? So case report on each day is only a fraction of the total infected on that particular day, okay? And yeah, okay. Now, if you think about it, there are other people studying epidemics, say epidemiologists or statisticians, right? So they basically, there's these methods, really systems, very well developed methods in epidemiology, infectious disease epidemiology, to analyze these data. Okay, they're basically their concepts, their methods are all developed based on the data. Where mathematical epidemiology, if you think about the theory, come from, I don't know, since probably at least well-developed 50s, 60s until now, we rarely look at the data. These theories of development are independent of the data, okay? It's based on infections. It's infected, new infections. We never talk about cases. Sometimes we call infection cases, but that's sort of a misconception there, okay? When you talk to public health, when they say a case, they mean someone they catch. Where when we say case, it's just somebody infected. So this is really different concepts. And so now we're at a phase where we have to connect the two. We have to confront our model with the data, with the cases, and a lot of problems happen. Okay. Let me show you one classical textbook example. I always wonder why people always mix the two. Okay, we should understand they're different things, and then I find out why. So this is a page taken from a well-known mathematical biology textbook, and it's a little example when we talk about SIR model. This is about a flu epidemic in a boys' boarding school in the UK, in England, in 1978. If you search this sentence, you find thousands of records, and in textbooks, in people's lecture notes, at different levels for undergrad students, for grad students. People use this. This is a very, very popular example. And how do you, because it has the data, and then you can actually fit your model very well with the data. So, okay. And these are the data, okay? And we fit the IT curve to that. For example, here in the textbook, it says that the boys, when they're infected, they will put to bed in a small hospital. So we have the IT directly from data. Sounds reasonable. So we fit IT to the data that's a given, and then you produce this. And you estimate the parameters here, it fits perfectly, right? So that's why people really like this. And I was curious as I went back to this medical paper published in the 1978 in the British Medical Journal. This is the data, the curve, right? This is the curve. These are the dashed lines or dotted lines are for you recovered. So these are the people who are sick. These are the people who get into the hospital each day. Okay. So here I zoom in a little bit. Okay. The graph, okay, there are two graphs. The solid graph shows daily total number confined to bed. Okay, confined to bed. And then the other ones are recovery. Okay, and total, there will be 83% of boys. Overall, there are about 760 boys in the school. There are 80% of them infected. So that's a quite large epidemic. But these numbers tell you are the number confined to bed. Okay, but think about it. What is I? I's are number of infected each day. If we think all of these infected on that day are confined to bed, then you wonder who infected the people tomorrow or the day after. These people confined to bed, they're not capable of infecting anybody, right? If you think they will infect the nurses and nurses infect others, it's actually, the paper actually said, you know, about 130 adults, there's only one that's infected. So it's not through the nurses. So you find that, you know, if you kind of characterize your IT, you got a problem here, right? So this is mismatching of our model terms in our equations to data. So how do we actually set up should we set up an epidemic model? So you have to see the infected in two categories. I always thought that iceberg is a really good metaphor for that. And this is not, you know, a lot of people use this. So the top part is what you can observe with epidemic. This is just a snapshot of the epidemic for a particular day or particular week. Okay, this picture changing every day, but we just take a snapshot of it. So on that particular day, there are people who are already known to the health system. These are the cases, active cases. And underneath are the people who are infected, not known to the public health system. So I call this part IFT. IFT for me is people who are hidden, who are infected but hidden. So these hidden people infected others who showed up in the hospital maybe tomorrow or the day after. Not these people on the top. These people are isolated in the hospital. They're not capable of infecting anyone, right? So because there are people at school or in the communities that are infected and infectious that are not known to us, these people are at large. They feel free to walk about, they can infect others, and then those new infections will show up in the hospital. So assuming that IT or everybody in the hospital, you're assuming that the public health system knows the entire iceberg, which is totally not the case. If you talk to public health people, they know this is not true. And there are people in the communities are infected and they don't know, and they don't know who they are either. Okay, so this is a sort of, yeah, the total is all the number of infected. The top is the active cases. known to the public health system, and this is the underneath. The underneath part is what our model is trying to capture. The epidemiologists just work with the tip of iceberg, but we wanted to use the tip of iceberg to inform us of the underneath. The underneath predicts the future tip of iceberg. So this is the way I see the. So okay, I think I should. Okay. So I'll probably just explain this. So in order to really take the data into that, we just have to add a cases compartment here. So we have SIR cases. So when you're infected, you can recover naturally to cases, but you might get tested, okay? And then you become a case. The compartment that known. Everybody in there are in the public health system. They have a data on that. And the rest over here, they're just hidden. Okay. So row I, this flow, row I here, row times I, is the daily new cases reports. This is the data. We're fitting this flow from I to C to the daily case data. Okay. So the row here, this testing rate here, is basically the number of new cases on that day divided by the current number of hidden infections, IFT, on that day. So this is dependent on T, this is dependent on T. The ratio, we call it the case infection ratio. So if you look at this, you probably think rho T should be depending on time, should be time dependent, shouldn't be a constant, okay? So now, would this be a better model? Would it perform better than SIR? Nope. So let's just quickly do 2 test drives. Here, this is what we did back in April during the first wave. Okay, we look at the Australia first wave, COVID in 2000. So these are the daily cases. This is the cumulative cases. The total is less than 7,000 cases total. Very mild first wave. So what since we have the entire epidemic curve, we fit our SICR model to that. And then this is the cases. This is our model kind of fitting. So the blue curve is out of our model. It really wraps around this case data, tightly. And the parameter estimation, the posterior is so concentrated. So it's a really good fit. Now, so you would say that the model reproduce the past, right? And can we actually predict what is that actually true? So we can only say our model reproduce the known part of the past, observable part of the past. There is also a hidden part of the past. So we have to look at that. So you just plot ST and IT here. So this is the ST. So you can see the final size here. This is S0, this is S infinity. So this is how much you lose. So therefore, this is the epidemic size. If you look at the proportion, it's 80%, okay? So this part, you lose 80% of your initial susceptibles. That's the epidemic size. And we shouldn't be surprised. This is definitely, there are only 7,000 cases total, and there's 25 million people in the total population. And we say, well, 80% of them all infected. Nobody would believe that. Right? So we didn't reproduce past. The good data fitting to the cases, you only reproduce the tip of the iceberg time series. Not necessarily reproduce the underneath part. We usually failed underneath part, badly failed. Okay, the 80% is not really surprising because the R0 is around 2. So that final size parameter tells us it should be 80%. And that, there you go, you see that, right? So even the well-calibrated SICR model has no predictive power here, basically. And you can also do another test, if you don't use final size. statisticians knows, you can do cross-validation. So you separate your data into training data and the validation data. So we did that. We used the data before the peak to train the model, the good fit. We estimate the parameters, and we try to predict the data after the peak. So the prediction, here's the peak in the data, predict that the peak is here. It's much higher, much further away. So if all of us do this kind of cross-validation to our model, we'll see the model is not right? It doesn't do things right. Okay, so lesson 2 here is that even mechanism models need a validation using either independent data like final size or cross-validation. We need to validate. We need to validate our model before we do the prediction. Okay? The good fitting to past data is not model validation. You need to do other kind of model validations. That's another lesson. And also there's the reason that we see these things happen is there's a non-identifiability if you include the data part in your model. Now let's think about the model fitting process. Okay, so we're using the daily new case as data because that's how it's reported. We identified this many new cases today. So, and that's a row times IT in our model. So this is the flow from underneath parts to the top through testing. Okay, and you kind of look at the error between the model output and the data on all the time points that you want to minimize, find the beta row, minimize that, right? So, or if you take it roughly, you try to make row times IT roughly equal to data T over the data. But data is what we know. We don't know row. We don't know IT. We know the product. So to find the row or beta is like constructing a rectangle, but only knowing the area. So there are infinite many beta row combinations that will give you the best fit, but they produce very different outbreaks, epidemics. I have 2 sets of the beta and row. They produce equally good fit to the data, but they predict very different epidemics. So this is a non-identifiability. This is the inherent. It's inherent to what we do. Okay, how to overcome that is also a huge challenge here. Okay, now if you think that you make the model more complicated, this might go away. In each complicated model, there's a little SICR model embedded in it. So you only make this problem worse because you have to fit so many more parameters. Right? So this is something that we really have to face. If we can resolve this, so there's challenges that we have to get better understanding of real-world epidemics. So asking the basic questions that what are the important drivers that collectively determine when the epidemic peak or end? Why does the epidemic peak at a certain time? Why wouldn't it go any higher? Our old theory tells us, well, you lose so many susceptibles. But the theory actually basically tells us you have to lose half of your susceptible for it to peak if R0 is wrong too. You have to get half of your population infected before the peaks, but that's way too much, right? So there are other factors are in play. So we have to understand that. And about our theories and models, we have to improve our theories, but overcome these 2 challenges, the final size challenge, we overpredict the final size, and non-identifiability challenge. These are, I call it iceberg challenge. We have to face that. And so I guess I'll probably just take home message that, so modeling is a powerful tool for studying epidemics because our models are only ones they're looking at underneath part of the iceberg, which is really the driver for epidemics. If you only look at the top, you don't really know why tomorrow is higher. So our model is really, really important and should be very powerful. And the standard theory somehow kind of missed a lot of the drivers in the real epidemics. We needed to look at them, understand them, improve our theory accordingly. And so there is a iceberg is a good way to see it, understand that. And so in the past, because we have this mismatch, we match the IT to the tip of the iceberg instead of the underneath part. These non-identifiability issues just got covered up. We never realized there's that. But if you look at it correctly, you see this. This is actually very, very difficult thing to do, right? So, and I think I'll stop here, and I may be able to answer a few questions. Thanks very much.
Thank you, Michael, for your